Hello everyone. I'm Moshe Shadmon from ScaleDB. I'm the CTO and founder of ScaleDB. And I'll be talking about our storage engine. I'll try to describe, to focus on two features, or two technologies, which are different than the technologies that exist in other storage engines. And the first one is our clustering solution. What we offer is a way to connect multiple nodes over the same physical database and share the data among those nodes of the cluster. And the second technology, which is different, is our indexing technology, where we have an approach where a single index could index not only the data, but also the relationships between the data. We call it a multi-table index. And I'll be talking about those two technologies, and we'll also demonstrate those technologies, how it works in an engine which is plugged into MySQL. So just as an overview, just to be in perspective, ScaleDB is a storage engine for MySQL. It uses the storage engine API in the same way that MySQL communicates with InnoDB or other storage engines. It communicates with us, and but the main differences, as I mentioned before, we use the shared everything approach, or it's a shared disk approach. And the second thing is the multi-table indexing. It's a transactional storage engine. We support row-level locking. It's ACID compliant, and it's a disk-based storage engine. And the last bullet, disk-based storage engine, the point that I want to make is that we address, or the target is to address the largest data sets. So it's not something that assumes that either the data or the indexes resides in memory. It's targeting at the largest data sets where you are also dealing with issues of how much to cache and what to cache and so on. But in this talk, I'll try to explain the first two main points, which is the clustering and the indexing approach. So when we're talking about shared disk approach, the first question that would pop up is, what is the main differences between a shared disk approach and a shared nothing approach? I mean, the only current way to handle clustering today with MySQL is with a shared nothing. And so when I talk about and try to explain the differences, the things to keep in mind is, what are the manageability, the availability, scalability, and performance implications of either approach? So we start with the issue of clustering pops up once we have our database, and for some reason the database starts to be exaggerated. I mean, it could be because our data sets are very large, or the number of users that try to use the database exhaust the database. And so the question is, what can we do? And with shared nothing, what we do is we say, okay, I can't really scale with a single node. Let's partition the data, and let's use multiple servers. Each server would be responsible for some amount of data. So one way to partition the data is simply to take different tables and place them on different servers, and then when a query comes and when the user wants to do something with the data set, we would have to direct him to the particular servers that carries the data. Now, it seems logical, but it's not that simple. There are many problems with taking this approach. For example, I might have a few tables. Some of them are very big and consume a lot of the processing power, whereas some others are very small. If table B, for example, is the big table that attracts most of the traffic, partitioning it by splitting different tables to different servers wouldn't really solve the issue. Another issue that shows up is how do the user distribute their calls against those servers. So even if I was able to find a way to partition my data in an efficient way, I still need to consider how would the user exercise the data. It might be that although the data is evenly distributed, all my calls would go to server A or to server B. And again, this way of partitioning wouldn't solve the problem. So if we're doing a shared nothing, there is a whole set of questions or issues that rise, and we have to handle them. And it's very difficult to predict the usage patterns. It's very difficult to avoid data skews. We get into situations of two-phase commit where my updates cannot be completed on a single server. I have to go to another server, and then I have to synchronize the transaction between those two servers. So it's a complicated task. Another way to partition the data is by what's being called horizontal partitioning, when we try, in order to cope with some of those problems, to distribute the data not by table, but by some other criteria. And usually this criteria tries to be random, so that the distribution of both the data and the queries would be even across all the nodes in the cluster. So here in this example we've distributed the data according to the salary. So all the salary that, if we take a salary divided by 3, find the remainder, and then that determines which node this row of the table should live in. So if we take this approach, the data would be distributed evenly, and also there is a good chance that we can distribute the calls of the users in a reasonable manner. However, there is a whole set of problems that would raise with this approach. Some queries could be satisfied well. So if I'm looking for all the people with a salary which is 60K, that would go directly to the node that stores those salaries. However, there is a whole set of queries that cannot be satisfied by this partitioning. For example, if I want to have a range query, now my data is spread all over the servers. If I'm trying to do a query my query predicate is not something that determines the partitioning, I have to send the query to all those servers. Another problem that usually exists in a situation like that is we send the query, even if we're able to hit the correct server, we might need to join some data that resides in a different server. And so now we have to communicate between the servers. So there is a whole lot of problems with partitioning the data and trying to scale in a shared nothing approach. So our approach, it's called the shared disk, and it takes a completely different view and trying to solve this problem completely differently, where we say, okay, our data set grows. Our solution is to place multiple nodes that they all share the same physical data. If we're taking this approach, there is no need to partition the data, and I can scale very easily. So I'll show you how that works in just a few minutes. But before doing that, let's look at shared nothing from a different perspective or a different point of view. So I have my nodes, in a shared nothing architecture, and every node has a particular type of data within the node. Now, when I have my users, the users send queries, and I need to figure out which node should execute the query depending on the content of the query or the result set that the query needs to satisfy. However, we cannot, in many cases, we cannot complete the execution of the query in a single node, we might need to join data. Sometimes the data is spread across multiple nodes and so on. So that complicates the issue. And in addition, we have the problem of a failure. If one of those nodes failed, I lost all my data. I cannot access my data anymore. And therefore, I need to do something which is to have some replica or duplicates. This is done by slaves. So I have my master databases on 3 nodes, and I need 3 slaves that would hold a copy of the data just in case that one of the nodes would break. If I'm doing that, I need to do another thing, which is to constantly synchronize between those masters and the slaves, so that in case of a failure, I'll be able to maintain my data and redirect my users to the slave machine. Not only that, I have to do some adjustments and let the existing nodes talk with the slave now, not with the master, because obviously the master is not able to respond to any calls. So there is a lot of overhead in maintaining the structure. This solution is also raises question if we want to scale. I mean, let's say that I have more users suddenly, and those users are now trying to use a particular node. It's very hard to scale. I mean, the only way that I can deal with this thing is by saying, let's repartition the data and let's consider the new usage pattern that was noticed. And the same problem exists if my data grows. It might be that on one node, the data would grow disproportionately to the other nodes. Again, the way to deal with something like that is to repartition the data. With a shared everything, or with a shared disk solution, those problems do not exist. And so if I lose one of my nodes, I can simply redirect my call to the surviving nodes. And the reason is that all the nodes share all the data. They have access to all the available data. If I need to scale the system, all I need to do is add additional nodes to my cluster, and those nodes have, again, a unified view to the data, and if I have additional users, I can send them either to the new nodes that I added or to any one of the existing nodes. The assigning process between a user and a node is much more simple than in a shared nothing, because it doesn't really matter which node would satisfy, would take over this query, this user query, and so it could be done in a round-robin manner, or there are many simple algorithms that can be used. In the same manner, if my data set grows, again, it's not an issue with a shared disk solution. So before we saw a demo on shared disk, just to summarize the differences, so we can grow by just adding nodes to the cluster. Servers can be added and removed dynamically. There is no interruption or minimal interruption to the application. There is a much better availability than in a shared nothing environment. And all of that significantly impacts the total cost of ownership of the entire system. Before the demo, one more issue. So we've got we've got MySQL, and we've got the storage engine attached to MySQL. And the question is, how can we make MySQL operate over in a clustered environment? As MySQL has no knowledge and no info about additional servers that might update and change the data. Somebody has to make sure that the integrity remains among all the nodes of the cluster, and in particular, we've got one data set. So if we look at the architecture, we've got the ScaleDB engine, and the ScaleDB engine has several components, including a cluster manager, which maintains what we call a global lock manager that can synchronize the processes not just within a single node, but among nodes in a cluster. There is a communication layer that can communicate to the storage device and also to other nodes that appear in the cluster. So if we think about operations like insert, what happens is that the user sends an insert request to MySQL. MySQL processes the insert in exactly the same way that it would process an insert for a single node engine. When we get the call into our engine through the MySQL API, we do two things. The first one is we make sure that the things that needs to be updated can be updated. If another node is updating the same piece of information, we have to know about it, and we have to not allow it so that we wouldn't have a conflict. If one node wants to update the salary to 70K from 60K, we don't want to let another node update the salary to a different number at the same time. We also have several mechanisms that would minimize the traffic. On one hand, we've got to synchronize between the nodes. On the other hand, we don't want to circle requests all the time. So those are separate components which are not seen on the drawing, but they try to minimize the traffic. And there are many cases where we could know if it's possible to update or not without sending messages between the nodes. However, in some cases, we need to send messages, and once the engine decides that the operation can be done, the insert would go in and update the files. A similar process works when we do queries. So if a user wants to query, sends their request to MySQL. MySQL, again, doesn't know that there is a cluster. It thinks of a single node. It goes to the engine. The engine, if it's needed to be synchronized with other nodes, it would be synchronized. And then when we know that when we know that we could pull the data, we would pull the data and send it to the user. And obviously, the inserts and the queries could be done from multiple nodes simultaneously, which allow you to have a much better throughput and scalability than a single node that operates over the same set of data. The last example that I would give is relating to create table, which raises another interesting problem. So when the user creates a table or changes a table, or does a type of DDL type of operation, we have, again, an issue where this thing is known to a single MySQL instance. MySQL maintains the metadata about all the tables and all the structures that are maintained in the database. And the problem is that if this table was created on node 2 in this example, the problem is how would an insert or some other operation that would want to use table A that is using node 1, how would it know about a table that was created on a different node? So the way that we handle that, we take the create statement and we let MySQL do whatever it does. So he creates the metadata on node A. But we got the SQL statement. We use our link or gateway between the different nodes, and we pass the create statements exactly in the same format that it was introduced to node 2. We pass it to node 1, And the engine appears to node 1 as a regular user that creates the same table. Once we do that, then table A, node 1, has the same metadata as node 2, and our queries and inserts that use table A could come in by either of those structures. We're getting to the demo in a minute. In terms of the installation of an engine, it's very simple. It's very straightforward. It would be like installing any other engine. We've got a config file that you have to put in the same place where the MySQL config file. And there is some extra info that we need. For example, the IP addresses of the machines so that they can communicate the place of the directory that contains the log files. And the reason for that, if one of the nodes fails, then the other node, the different node, takes over the log file and rolls back the uncommitted data. So we have to know, every node has to know not just where its own log file, but where any of the other log files exist. But it's a very simple and straightforward installation. I mean, it's a 5-minute process to install a cluster system with ScaleDB. So I'll turn over to Ron Hu, who's our VP of Engineering, and he'll do a very short demo that would show you what is the effect of using a cluster system.
Okay. So first, let me kick off the MySQL sysbench script. Okay, that's on node 1 and node 2. Okay, so here we connect to a cluster machine in our lab. Okay, and this cluster machine contains 2 servers, basically 2 nodes. And in the top window, it connects to the node 1. Okay, and in the second window, this one we connect to the node 2. So, and here we wrote a simple wrapper on top of MySQL sysbench program. So here you can see that this is the total aggregate throughput per node. Okay, and we run about 10 concurrent users without any think time. I mean, so basically, try to maximize system throughput. And then in this test database, we have a sysbench table with 50 million records. Okay, it's now over 10 gigabytes. Okay, so you can see that on each node we can get more than 400 transactions per second, and the total system throughput is, you can say, is about 900 transactions a second.
So.
Yeah.
Thank you, Ron. Now, so just by adding another node, we're able to double the throughput, and we didn't have to partition the data. We didn't have to go through the process of considering what would be the user patterns, what would be the data patterns, and so on. We just added another node, and we are able to benefit from those advantages. So the next topic that I'll talk is our index approach, which is also very different, not only from the indexing that is being done within MySQL engines, but also it's very different from the indexing which is done in commercial databases. Actually, all the database companies are using the same index structure, which is called B-tree. The difference between the companies is in the way that they implemented the B-tree. But conceptually, it's the same structure. Everybody is using the same structure. Whereas we took a different approach. Our approach is based on a structure which is called Patricia tries. I wouldn't go now in this session to the details of how the trie is built and maintained. However, if somebody is interested in more info, on those tribes, there is a lot of information and white papers on our website. So conceptually, you could say that B-tree address only the data. You would use the B-tree file to find a row by a key. So you've got a customer with the customer ID. You would use the B-tree to pull up the customer information by the key, by the customer ID, by the customer name, whatever the key field is. But that's what the B-tree does. And we've done something which is, we added another dimension which does not exist in B-tree. We map not only the data, which means we not only can bring the data by the key, we can also maintain the relationships between the data. So if we search for a customer, and the customer has information which relates to it, it's got invoice information, it's got Word documents that relate to this particular customer, we can find all this information by the same index structure. So what are the advantages of this approach? The advantages is that this approach is faster. You get better performance, and we also have a demo that would show you where we would show you the effect in terms of performance of using our indexing approach. Our index is much smaller in size, so you get, for large systems, you get a much better cache-hit ratio, so that helps you in performance as well. And it also maintains the referential integrity. So if you say, I've got a customer and an invoice, and the invoice relates to the customer, when you insert the invoice, the system would make sure that the customer exists. And it maintains the referential integrity without the overhead that you would get if you would want to maintain the integrity using B-tree. The B-tree approach would say, okay, we're inserting an invoice for a customer. Let's go to the customer index file, pull up the customer, and see that the customer exists. Whereas here, since the relationships are mapped inside one index, when I insert the invoice, the path to the invoice includes the path to the parent, to the customer, and therefore I'm able to maintain the referential integrity almost for free. And so that approach also helps me not only on the queries, but also on the inserts of data. So
it seems to me like if a customer had thousands of indexes and you did, customer had thousands of invoices and you updated the invoices, don't you have to redo your entire index structure?
No. We go directly. In that sense, we work very, very much like B-tree, where it would lead you to the place that needs to be retrieved or updated. But this place has additional information. It can show you, it can continue the path to the particular invoice. So you would have a particular customer, and a particular invoice that you would want. The index would take you to both of those, and to both elements in a single path, in a single traversal. Yes?
Can you go back to the previous slides? So obviously there's advantages of doing this index and the relation and referring to the primary key forms itself. However, in the large-scale installations in our typically DBA, they don't like to have the only key constraints. So they typically disable it, and that's happening in many environments.
Right.
So in that case here, what is the advantages having using your whatever the index you have compared with the conventional B-tree?
Right. So if you don't, what we're trying to do is, in terms of the indexing, is to say, okay, I've got queries which are complicated. Let's try to address those queries in a more efficient way by building more intelligent indexes. And then the second thing that we do is we say, not only that, let's do it transparently. So the user doesn't have to say anything. We'll take the current definitions and build those indexes transparently for the user, for the DBA. If the user does not tell us that there is a relationship between an invoice and a customer, we wouldn't be able to guess that, right? I mean, there is no way to guess it. So you remain with an index which is built on tries, not on B-tree, over your data. So there are differences and there are advantages to use just those B-trees, but they are not so big as if you were to add the relationship. So one of the advantages is that the index is much smaller. The index is not sensitive to the size of the key. It's all the cost per key that you maintain in the index is fixed. So you could index URLs, very large URLs, 1,000 bytes. The index would still increase for every URL that you would index by just a few bytes. So there is an advantage. You will get a much better cache ratio because you could put more into cache in terms of the indexing. But yes, if you don't tell us about the relationships, we obviously cannot take advantage of that.
Can you give us a relative index ratio, taking, for example, the B tree on one extreme and bitmap index on the other extreme, which are very, very compact. And what is your savings in between the B tree and the bitmap index?
Right. So a bitmap index is not a real comparison because the index that we have is it's generic. It supports range queries. I mean, it has the same functionality of B-tree. In indexing, I mean, there is a trick. You could do things extremely fast, but in order to do that, you have to make specific decisions about what you're not going to support. So you could take a bitmap or hash tables that would work very fast, but then range are not supported. So we're in the family of a general purpose index, where there is a set of things that needs to be supported, and we're not eliminating anything. We need to support range queries, we need to support point lookups, and we need to do it efficiently. So putting us and comparing us to a hash table or a bitmap is not the right comparison.
I'm not talking about the mechanism, I'm talking about the slices.
Okay,
so what you're saying is that your product gains advantages by reducing whatever the argument you're using in the index that you store and make much more compact and much smaller footprint. So I'm trying to get some perspective ideas about what is the relative comparison between B-tree versus bitmap and what is your scale here?
Moshe, can I help you answer the question?
Sure.
Okay. Yeah. Because we have done some benchmark. Okay. It's for the same kind of index we build on using B-tree and also using our data structure. Our index size is about 25% of a B-tree. As for the bitmap, one thing you need to consider is the cardinality. How many of a unique value you have? If you have many unique value, then bitmap index size can be reasonably large. Okay. If you have a very small number of a unique value, then bitmap is very compact. I would say that if your cardinality is small, then bitmap index can be smaller than our index size. But Moshe's point is, in terms of functionality, if you want to do comparison, we usually just compare with B-tree because we can do whatever B-tree can do. But bitmap will be more difficult to do some of such conditions.
So let's take an example. And so the example that we have, we want to join information between enrollment of students to different courses in different colleges. So we see on the left side, we've got the select that joins information from 3 tables. And I'll go over 3 different ways to satisfy this type of query. So the first one would be a conventional join, and that's what MySQL does, and most databases do. So we would pull up the enrollment information, and then we would pull up the course information and the college information, join all of those together, and bring it to the user. So I would have to use three separate index files to satisfy this query. The second approach is by doing a materialized view. Now, MySQL does not support materialized view, but commercial databases have implemented materialized view. In materialized view, what you do is you build a new table, which is the aggregate of the source table. So in this example, this new table would have the college information, the course information, and then enrollment information. And as you can see, there is a lot of information which is redundant in this table. It becomes a huge table that can satisfy the query very, very efficiently. But in the cost of having an additional table that needs to be maintained, and not only that, it constantly needs to be synchronized with the source table. If I change my student address, then not only I have to change it in the source table, in the student table, I have to go into the materialized view and change it here. So this gives us great performance. I can go directly to the place that contains all the data, but there is a cost. And usually people use this approach very, very carefully. There would be just so many views that would be maintained, and it's always the cost of maintaining the view is considered against the performance advantage that you would get. So we have a different approach that we mentioned here, and I'll show you how we work. The first thing, we capture the relationship. So if in the example, when we create the table, we know, okay, we've got a college table, and when we created the department table, if there is a referential integrity, if the department table declares the college as a foreign key, we know about the relationship between the college table and the department table. If, again, there is a create statement of the course information with relationship to the department, we know about it, and so on. So once we capture this information, there are two things that we do or consider. The first one, we do not want to create this view physically within MySQL, within ScaleDB and maintain it. It's too costly. So on the other hand, we want MySQL to know about those relationships and operate efficiently about them. So there is a gap here between the information that we know and the information that MySQL knows. And the question is, how do we bridge between those two things? So the way that we handle it is we first identify those new views or relationships that needs to be maintained. And as I showed, we can capture it from the primary key, foreign key definitions. The second thing is that within our space, within the engine space, we just keep the source table. We don't create this view. However, we tell about those tables, about those additional tables to MySQL. So MySQL metadata in this example would have 9 tables, whereas ScaleDB would have just 5 tables, which are physically stored on the disk. So we can see that college department course table doesn't physically exist. Same with college student table, and so on. So we have a difference here between the physical storage that is maintained by the storage engine and the metadata. Now when we have a query, we say, okay, we don't need to use those tables to satisfy the query. Let's use a new table which we create, again, transparently into MySQL that describes the relationships. So there is a set of a few such tables that were created behind the scene to MySQL and triggered this new metadata that we define in the MySQL space. Once we have that, we could use simple query to this virtual view, to this new entity that MySQL is aware about and knows about and is not physically maintained in the engine. And so to the question, how do you satisfy those queries, when we get the query, we use our index. Since the index knows about the relationship, we can go directly to all the columns, to all the rows in the source table that are part of the result set, combine them together, and return the result sets to MySQL in a way that is identical to the way that would exist if we were to maintain a physical table. Okay. So the way that we operate, to summarize this process, we tell MySQL about those additional tables, additional views, which are actually virtual views. We don't physically store them at the storage layer, and we construct those views on the fly according to the query that comes in. So I was told that I ran out of time. So I think I'll stop here. If you have a question, I'll be happy to answer your question. I can also stay here after the talk. We have a booth. I don't know how much time we have there, but
you still have 5 minutes.
You want to give a demo?
Yeah.
Go ahead. So, Ron.
Okay. So here, let me give you a quick demo first. Again, we connect to the cluster machine in our lab. Right now, I try to run a regular, the regular SQL with a physical table. Okay, and this is the throughput we get. Here, we try to, in this college demo database, we have about 63 million records. And we try to simulate, every student, they try to get his grade, for a specific course. Okay. So here you can see, roughly the system throughput is about, between 50 and 60. Okay. And then if I use the virtual table, if we are use the multi-table index, the multi-table index is expressed in a virtual table format. If I do that, okay, so now you will see the system throughput. By the way, initially in the little bit slow, there's some code cache. Okay, here, basically you will see that the system throughput will increase. Occasionally you see that number is like kind of a little bit big, is because somehow for some records, if the records are cached in memory, okay, then you get the system throughput kind of high. And then the very next one, I'm going to run to use a virtual view and then run it on the cluster. Okay, on the top window, I submit the query to the node 1. On the bottom window, I submit the query to node 2. Okay, so you can see that we can basically increase the system throughput. We basically double the system throughput on our cluster machine, because both servers access the exactly same copy of the data. We have only single copy of the database.
So we have two layers of advantages. One is the indexing that gives you better performance if we can capture the relationships, and obviously we can expand that to a cluster environment where multiple nodes share the same shared data. So I can finish with this slide where we tested it with one of the engine which is comparable to us in terms of functionality, but I cannot say the name of the engine. And we took a simple query which does not we tried to do something which does not favor our approach. So lots of data was if one table was cached. I mean, we tried to do something which is reasonable and balanced. We got advantage because of using the indexing, and we got obviously advantage by adding another node. At the end of the day, we have like tripled the throughput by using the two technologies for this particular query. Obviously, for different queries and different data sets, you get different results. We're also in a beta mode. I mean, if there is anyone here which would be interested to try our product, we'll be happy to talk to him and work with him. So maybe I'll take one question, please.
Did you also have to benchmark on the insert side if there was any performance degradation?
Yes. So we also benchmark on the insert side. And the insert side, you don't, on the query, it's very clear, you clearly double. On the insert, it goes to 1.7. With another node, it could go to 1.7 again. It depends on the distribution of the data and the queries. So it's 1.7, 1.8, around those things. But it's really a matter of you taking and trying it on your data set and figuring out what's the advantage that you would get. So thank you very much.